This course provides a non-technical introduction to understanding the AI terms like machine learning, data science, computer vision, natural language processing, model deployment, etc. This short course is perfect for product managers, CEOs, and pretty much anyone looking to understand the AI terms without any technical or programming background. The instructor for this course is Ramsri. He is a lead data scientist with 8+ years of experience across Silicon Valley, Singapore, and India. Most recently, he had been a co-founder and CTO of a funded AI startup. And I am one of the AI avatars who will be assisting Ramsri in teaching this course content. Believe it or not, I am a synthetic voice with simulated lip movements generated from just text. Coming to the prerequisites, I am glad to inform you that there are none. Everybody can take this course, just bring in your enthusiasm to learn. Let's go over the course outline to know more about what you will learn in this course. First, we will understand what is AI and its applications in the modern-day world. Then we will understand what is data science. In the next section, we will go over what is machine learning and the subcomponents of it like supervised learning, unsupervised learning, and reinforcement learning. Then we will understand computer vision and natural language processing. In the final section, we will understand the concepts of training an AI model and deploying it. And with this, I welcome you to the course.
What is artificial intelligence? Artificial intelligence, or AI, is the branch of computer science that focuses on giving machines or computers the ability to think as intelligently as humans, and in some cases better than humans, learning from a lot of data. The goal of AI is to capture the collective intelligence of humans and do a given task better than any individual human can ever do. In the modern-day world, we see a lot of AI applications around us. One of the applications is self-driving cars. For those who are unfamiliar with them, I will explain more about it. Right now you have on-demand cab services like Uber, Lyft, etc. that take us from destination A to destination B. So in countries across the world, there is significant research going on currently where an AI system will use cameras and different sensors to navigate on the road and take us from destination A to destination B without a human cab driver. These are self-driving cars. And another example is language translation. You might have used Google Translate when you visited a new country to translate a given sentence in your language to a sentence in a foreign language. Another example is credit card fraud. If there is a transaction suddenly from a new country or from an unusual origin, there are AI systems built by credit card companies that flag it and send secondary verification to your email or phone number. And other examples are artificial voices like Siri, Alexa, and Google Home that perform tasks responding to your voice commands. Also, when you are watching a YouTube video, there are recommendations shown to you automatically, based on your previous watching history and several other parameters. These are AI systems in action to provide you with the ideal recommendations. Similarly, when you are shopping on Amazon or any e-commerce website, similar products are recommended to you when you are viewing a particular product online. In many countries across the world, there are facial recognition and fingerprint matching technologies that check you in at the airport or the office. All of these are modern-day applications of AI.
What is data science? Data science is a comprehensive process that involves data collection, data cleaning, data visualization, and using various statistical or AI techniques to solve a problem. Artificial intelligence techniques are a part of the data science process. Now that you understand AI on a high level, let's go a bit deeper in understanding AI and the different components of it. In the real world, you hear quite a lot of terms like machine learning, deep learning, computer vision, natural language processing, etc. In this course, we will attempt to demystify all these terms and also see how these terms fit together. The bigger umbrella is artificial intelligence, also popularly known as AI. Under it, we have sub-branches like machine learning, also known as ML, natural language processing, also known as NLP, computer vision, also known as CV. Then you have AI applications in robotics as well as any other areas like optimizing manufacturing pipelines, etc. Again, under machine learning, you have two popular sub-branches known as supervised learning and unsupervised learning. Algorithms like deep learning, decision trees, support vector machines, etc. fall under supervised learning. Under unsupervised learning, the popular type of algorithms used are clustering algorithms. We will go into detail in understanding these sub-branches of AI in the upcoming sections, so no need to worry if you don't understand these terms. Just register this chart in your mind on a high level so that you know how these things fit together under the umbrella of AI. Broadly speaking, if AI techniques are applied to text or speech, that field is called natural language processing or NLP. An example of AI applied to speech is Amazon Alexa. We can use voice commands to instruct Alexa to do a specific task for us. An example of an AI application on text is Google Translate, where we can convert a piece of text in one language into another language. All these AI applications on text and speech fall under NLP. On similar lines, the subfield of AI that focuses on applying algorithms to video or image to derive insights is called computer vision or CV, for example, face detection in our smartphone cameras. Machine learning or ML is the subfield of AI that mainly focuses on using data and deriving insights or predictions from it. Example, predicting future stock price from previous values or classifying a transaction as fraud or non-fraud using data of the transaction, etc. One important thing to note is that there is significant overlap among these AI techniques. For example, machine learning algorithms like deep learning, etc. are heavily used in natural language processing and computer vision to solve problems with text or images. We will get a deeper understanding of each of these terms in the coming lectures. Thanks for watching.
Welcome back. In this section, we will understand machine learning and the components of it in detail. Machine learning is a subfield of AI that uses algorithms to automatically learn how to perform a given task without being explicitly programmed with rules. Machine learning has three main branches under it: supervised learning, unsupervised learning, and reinforcement learning. Again, under supervised learning, there are different types of algorithms like decision trees, regression, support vector machines, deep learning, etc., which are used to solve a given problem. Let's take the example of how a small kid learns and apply that to understand these different sub-branches of machine learning. Assume that you have a fruit basket with several kinds of fruits. First, you show each fruit to the kid and tell him or her what it is called. For example, apple, banana, orange, pomegranate, etc. Then you give a new fruit basket and ask him or her to identify or classify the fruits in it. This is called supervised learning. You provided training examples, which are fruits in our case, along with their labels, which are fruit names, and the kid learns to map training examples to labels in his brain subconsciously. Then you use his or her previous learning to classify the fruits in a new fruit basket automatically. This is exactly similar to how an algorithm learns. Just like humans tune their brain, an algorithm tunes its internal parameters to map any given training examples to labels when shown with many samples. This is the training part of an algorithm. Once it is trained, it can later automatically classify any new samples, just the same way a kid is able to identify fruits and name them in a new fruit basket. This is also known as the inference phase of the algorithm, where it can classify any new sample shown to it. Under supervised learning, there are several kinds of algorithms like decision trees, support vector machines, deep learning, which are also known as neural nets, etc. You can assume these algorithms are like different brains. Each of them has its own learning capabilities and complexities. Identifying credit card fraud, predicting house prices, etc. are examples of supervised learning, where you use historical knowledge from training to learn and later predict the outcome for a new sample or data point. Let's take the same task that we discussed previously. If you give a fruit basket and ask the kid to separate fruits into different groups without giving any initial knowledge of what each fruit is called, that is called unsupervised learning. To simplify, you can equate unsupervised learning to the concept of clustering. In this case, the kid uses his or her intuition to cluster the fruits based on shape, color, etc. In the example shown on the screen, the kid first uses his or her intuition to cluster fruits based on their color and then by their shape. Here there are no explicit labels, that is, fruit names, given beforehand for each of the fruit in the basket. Still, the kid is able to segregate the fruits in an unsupervised manner based on certain characteristics like shape and color. Later, we can assign any label to each of the cluster or the grouped fruits. Identifying customer segments in shopping. spam versus non-spam, email filtering, etc. are examples of unsupervised learning. Giving a labeled dataset and training an algorithm versus just giving unlabeled data to cluster into a fixed number of categories is the main difference between supervised and unsupervised learning. If you let the kid learn a game by playing it, but not explicitly telling any rules, it falls under the category of reinforcement learning. You give a reward for every right action taken, and after several attempts, the agent, kid or machine, will learn to do the task automatically. Teaching machines to play games like Go, teaching robots to do a certain task automatically, etc. are examples of reinforcement learning. From the hierarchy, we have already seen that machine learning is part of artificial intelligence, and deep learning or neural networks is a type of algorithm within machine learning. Deep learning uses a set of algorithms called artificial neural networks that are inspired by the human brain. Deep learning is the closest algorithm that tries to mimic the human brain. Just like the human brain has neurons, there are artificial neurons that form a network in deep learning. Each artificial neuron is just a mathematical function that takes a weighted combination of inputs and produces an output. During training, the deep learning algorithm learns its internal parameters. Once trained, it can classify any given input or predict a certain value given some input. These small neural networks are stacked into multiple layers to form a deep neural network. While the idea existed for quite some time, we were able to train large-scale deep neural networks only in recent times because of the availability of compute power. So what used to be another algorithm called neural networks under machine learning rose to fame, rebranding itself as deep learning because of modern-day computing power. Now, deep neural networks are the fundamental algorithms that are powering machine learning, natural language processing, and computer vision. Most of the modern-day AI problems are primarily solved with deep learning, hence the special focus.
Computer vision is a subfield of artificial intelligence that uses algorithms to understand images and videos the same way as a human eye. Let's look at a few practical examples of computer vision in our real world. If you open up your phone camera to take a picture, a small square appears around every human face. There is a face detection algorithm running real-time and placing a bounding box around every detected face. Also, when you open Google Photos, you can choose a person's face, and all the images containing that person are returned to your Google Photos library. Similarly, Facebook auto-suggests people to tag when you upload a photo of your friends. Face recognition algorithms are powering these applications. Both face detection and face recognition are the core concepts of computer vision that helped progress the field from its initial days. Another important application is optical character recognition, also known as OCR. OCR is the technology to convert handwritten documents to digitized text that you can edit and modify, from automating the dispatch of handwritten postal addresses in the early days to digitizing old manuscripts. OCR has many practical use cases. Another interesting application of computer vision is the automatic tagging of images. All photo platforms prefer to automatically tag images so that you can later retrieve relevant images when a user types any given search word. Modern-day computer vision is quite evolved, but it is also enabling driverless taxis. Another interesting use case is image generation, where AI can dream up and create images of people that don't exist. You can check this website thispersondoesnotexist.com, and every image shown there is of a person who doesn't exist, but is created by advanced computer vision. Other use cases of computer vision are virtual reality and augmented reality applications. Mapping terrains using drones, and also an automatic visual inspection of tall towers or structures using drones are other interesting use cases of computer vision.
Natural language processing is a subfield of AI that uses algorithms to understand, interpret, and manipulate human language, that is text and speech. Let's look at a few of the applications of natural language processing. The voice assistants that we discussed previously, like Amazon Alexa, Siri, etc., are good use cases of NLP. You can say something in natural language and these voice assistants will understand and respond to you. So the first part is speech to text. Whatever is spoken by you is converted to text, and that text query is run on some search content, and the correct answer is retrieved and spoken back to you. Current progress in voice AI is such that it is hard to distinguish AI-generated voices from original human voices. Also, we can generate AI voices that can cry, express happiness, etc. Coming to another example of question answering systems, if a user searches for a query and you have a long document that has the answer, you can use NLP techniques to automatically retrieve the correct answer. Another example is text summarization algorithms in NLP. A given news article or book could be summarized into just a few sentences if there is no time to read the complete content. Chatbots are another popular application in NLP where the user converses with the chatbot and the chatbot replies back with an appropriate response. Sometimes chatbot understands the necessary intent and also does tasks like booking a flight or taking a pizza order from the customer. Understanding customer sentiment from chats and reviews is another popular application of NLP. Companies can quickly respond to customers who are unhappy about a product or service with automatic sentiment analysis detection systems using NLP. Another popular use of NLP is machine translation systems. Most of you might be familiar with Google Translate, which converts any given text from one language to another. All these are popular applications of natural language processing in the real world.
So far we looked into understanding artificial intelligence and its various applications. We also understood that data science is a comprehensive process where AI and statistical techniques are part of it. We also looked into sub-branches of AI like machine learning, computer vision, and natural language processing. We understood that machine learning is a branch of AI that uses algorithms to predict or classify a given outcome from raw data points or numbers. We also understood that computer vision is a branch of AI that deals with images and videos. Similarly, natural language processing is a branch of AI that deals with text and speech. Also, we understood that AI models need to be trained with data, and the internal parameters of the AI model are learned during training. Once trained, they are ready for real-world use. In this section, we will see the steps of AI model development. We will understand what is data and the process of data collection. We will understand what is noisy data and the data cleaning process. We will understand the topic of picking a model to solve a given task. We will understand model training as well as evaluation of the performance of the model. We will understand the concept of parameter tuning of the model if we want to improve the model performance. Then we will see model deployment, which is to make the trained model available for everybody in the organization or general public to use. Let's pick a real-world problem to understand the process of AI model development. Let's say we are given the task of developing a language translation system that translates any given sentence in English to a sentence in Spanish. So the end goal is to develop an AI system that takes an English sentence as input and generates a Spanish sentence that is the translation to the input sentence. So the first task is to collect a lot of data. The data in our case is translation pairs of sentences. So we need to collect lots of pairs of English sentences along with their Spanish translation pairs. It is ideal to see if such translation pairs are already available online. There is a possibility that someone else had a similar requirement and created these sentence pairs and made them available online. This is called a dataset. So essentially we look online to see if the dataset that we want to use is already available online. If so, we use it directly and do further cleaning if necessary to modify the data to our needs. But let's say you are building a language translation system specifically for hospital medical records text. Then you need to create the dataset yourself. What this means is that we need to employ experienced medical translators and have a system or process in place where they can easily convert a given sentence in English to a sentence in Spanish. Also, we need to execute it at scale, because if we need tens and thousands of translations to train our model, it is not practically possible to do with a handful of translators. Hence, there are separate tools developed just for data annotations, and some companies are built to provide just data annotation or data creation services. Depending on the task at hand, organizations can choose to have a small in-house data annotation team or outsource the data creation task to a third-party vendor. Also, the quality of any AI model is just as good as the data it is trained on. So it is very important to have a quality control process to remove noisy data that is, in our case, low-quality translations. This is the data cleaning process. One way is to have a quality control team where multiple people independently rate the quality of a given translation and later we only source the highest-rated translation pairs for our AI model training. In this way, we can ensure that we have high-quality data, and we are ready for the next step. Now that we have our data ready for training, let's discuss choosing a model to train your data on. A model is analogous to a brain. Just like different brains have different learning, memorizing, and recalling capabilities, similarly, different models have different capabilities. For example, let's assume you are a manager and you have a new project requirement and need to hire a new member to the team. You are debating whether you should hire a junior engineer or a senior engineer to learn and execute the project. While the junior engineer might not be accurate at performing a given task because of lack of experience, he or she is very economical. While the senior engineer might be very accurate, they might be expensive. A model has a lot of parameters that will be trained. As the parameters are just decimal numbers or integers, the size of the parameters determines the size of the model in megabytes or gigabytes when it is stored on disk. So in reality, choosing an AI model for a given task is finding the perfect balance between model size, the speed with which it generates an output given some input, the accuracy of the model, and ease of maintenance by other developers to retrain when necessary. Now that we have picked a model and also prepared the training data, the next step is to train the model. Training a model means showing data in batches to the AI model and making it learn. For example, in our case, if we have 10,000 translations, we group them in batches and show 64 or 128 translations at once for the model to learn. Since we already know what is the expected output translation, which is also known as ground truth, every time the model makes a mistake in its translation, we provide a mechanism for it to automatically update its internal weights. This makes the model get better over time as we show more and more samples and correct continuously when it makes a mistake. At the end of the day, text and images are represented as numbers before they are fed into the deep learning model. So a computer only sees a series of numbers and learns patterns from it. Just like students need to revise the curriculum and go through the content more than once to learn thoroughly, oftentimes AI algorithms also need to see the data more than once. One full run of the AI model through the complete dataset is called an epoch. We train our AI model through multiple epochs of the dataset so that it learns better. Well, we finally trained our model and are ready for evaluation. But what is evaluation? Just like we teach a kid during classroom sessions and later evaluate his or her performance in a test or quiz, we do something similar with AI models. From the complete dataset that we collected earlier during training, we set aside a portion of the dataset, usually 15 to 20%, to evaluate the model's performance once it is finished with training. This is also known as a validation dataset or test dataset, and we report our model performance metrics on this validation or test dataset. But what are these performance metrics? Let's take a simple case where you trained an image classification model that classifies a given image as a dog or a cat. You reserved 100 images in total as a test dataset that has 50 dog images and 50 cat images to evaluate the model's performance. Now, when you run your test dataset through the trained AI model, you realize that 5 cat images are misclassified as dogs and similarly 5 dog images are misclassified as cats. So out of 100 images, 10 images are misclassified, so you can say that the accuracy is 90%. But there is a small problem here. Let's say our test dataset has 100 images just like before, but this time we have 95 dog images and 5 cat images. Even if our model blindly classifies every image as a dog all the time, it is 95% accurate. This doesn't sound good. So accuracy is a good measure only if we have an almost equal distribution of classes. Otherwise, accuracy is not a good measure when we have an imbalanced dataset, like in our case where 95% of our test dataset is just dogs. Precision and recall are better measures than accuracy. To understand precision and recall in simple terms, let's take an example where we have 100 images with 95 dogs and 5 cats. We pass the images through our trained image classification AI algorithm, and it classifies 93 out of 95 dogs as dogs and misclassifies the remaining 2. Similarly, it classifies 2 out of 5 cats as cats and misclassifies the remaining 3. The precision for dog class is defined as the proportion of images that are classified as dogs are actually dogs. So in our examples, 93 dog images and 3 misclassified cat images are identified as dogs by the AI algorithm. So a total of 96 images are classified as dog images. And among them, 93 images are actually dog images. So precision is 93 by 96, which is equal to 0.968. So precision for dog class is 0.968, which also means that when our AI model predicts that an image is of a dog, it is correct 96.8% of the time. Let's calculate precision for the cat class. Out of 4 total images that are classified by our AI model as cats, only 2 are actual cat images. So precision for cat class is 2 by 4, which is 50%. So when our artificial intelligence model predicts that an image is of a cat, it is only correct 50% of the time. Similarly, recall for dog class is defined as the proportion of dogs in the original test dataset that is classified correctly. So in our example, 93 out of the total 95 dog images are identified correctly. So recall is 93 by 95, which is 0.978. In other words, our AI model correctly identifies 97.8% of all dogs. Similarly, recall for cats is the percentage of cats in the original dataset that are classified correctly. In our example, 2 out of total 5 cats are identified correctly as cats. So the recall is 0.4. In other words, our AI model correctly identified 40% of all cats. So evaluating an AI model means getting these numbers like accuracy, precision, and recall for our particular use case, and choosing if our current AI model meets the criteria. If not, we go back to the drawing board and see if we need to use a different AI model for training, etc. Now that we have seen how to evaluate an AI model, let's understand the parameter tuning of a model. If we give a big textbook to a student and ask him or her to learn it in 2 weeks, they might be able to only skim through the chapters. When we put them through a test or quiz at the end of 2 weeks, they might perform very poorly due to lack of time. Similarly, the learning rate of a deep learning algorithm can be controlled. So after evaluation, if the trained model is not very accurate, we can play with a better learning rate and see if the performance improves. Unlike the real-world example, we can also play around with the architecture of the neural network a bit by increasing the layers or decreasing them to see if the performance improves. We also show our samples in batches as mentioned previously, for example, 64 or 128, etc. The batch size can also be modified to alter the performance of the model. So these parameters like learning rate, batch size, etc. are called the hyperparameters of the model. These hyperparameters can be further tuned to improve the accuracy, precision, and recall of the model. And usually many experiments are done by changing the hyperparameters, and the configuration that yields the best performance is finally used. Now that we have finished parameter tuning and retraining of our AI model, we are ready for our model deployment. What exactly is model deployment? So far, an AI engineer would have been developing and training the AI model in his or her personal computer or a machine available on the cloud. Once the AI model performance is satisfactory, it is time for the AI model to be available for use by everybody. In our example, once the language translation model yields good results, we want it to be available for use to the general public or to the whole organization that we are working in. So the goal is to make available or deploy the model in the cloud so that a larger group of people can use it. For example, the translation model can be used by thousands or millions of simultaneous users. Sometimes the demand might be less, and at other times the demand could be more. So the system should also scale dynamically to accommodate the number of users using it. A good deployment infrastructure should make sure that a system is highly available and scalable. Top software companies provide tools and services to facilitate the same. For example, Amazon provides a suite of services known as Amazon Web Services or AWS, which one can use to deploy the model on the cloud and scale as necessary. Similarly, Google offers Google Cloud Platform, and Microsoft offers Azure. There are also several other companies providing tools and services to deploy an AI model to production. The subfield of AI that focuses on deploying, managing, and scaling AI models in production is called MLOps or machine learning operations. Outside of artificial intelligence, this field is also known as DevOps, development and operations. It is the combination of tools and practices to deploy applications fast and make them available at scale to the end users. In this video, we have gone over the concepts of model deployment and what it means to make an AI model available for hundreds and thousands of users. In the real world, humans exhibit traits like stereotyping and discriminating against people based on their age, race, and gender. Any AI algorithm is just as good as the data it is trained on. Since the data that we train our AI algorithms is obtained from the real world, it is highly likely that the trained algorithms also exhibit and mimic the bias that exists in the real world. The gender and racial stereotypes also propagate to the AI models and affect the output of the model. Imagine an AI resume classifier that always prioritizes a particular gender over others, even if all the remaining credentials are equivalent. It can very well make biased hiring decisions. Similarly, imagine a facial recognition system that is trained to identify crime suspects. It might be biased to a particular race if it is trained with biased data. So it is important to take measures to counter the algorithmic bias exhibited in AI models. While the following measures are by no means exhaustive, they can be adopted to mitigate bias in AI algorithms. Anonymize racial and gender information from training data. This can help mitigate the bias induced because of these parameters. Build teams with strong gender and racial diversity. This can help ensure that unintentional biases are caught before they make it into production systems. Build artificial intelligence models with explainability. If AI models are designed to explain their predictions, any biased decisions could be caught by knowing the contributing factors to that decision. Everyone building AI products should be cautious about the possible repercussions of their AI models and work towards building responsible AI products.
One way to train a model is to train from scratch with hundreds and thousands of data points, for example translation pairs in our case. But in the real world, learning happens through the transfer of knowledge from previously learned tasks. Let's take an example to understand this. In our previous example, when the kid had never seen any fruits in his or her life, perhaps we needed to train with a lot of fruits for the first time. Also, it takes a lot of time and effort to learn the fruit names and classify them when it is done for the first time. But once the kid masters and learns the task to identify fruits, the next time when we visit a new country and show a new fruit, he or she will be able to register and recall it later with minimal effort. So the kid uses his or her previous learning to classify fruit based on size, shape, and color, etc. A similar concept used in AI is called transfer learning or fine-tuning. Similarly, let's take another example to understand this better. Let's assume that you invented a new game similar to football or rugby and are looking for players for that game. Usually you don't go out in the wild, find and train players from scratch. You find athletes or previous players of football or rugby and train them for your newly invented game. We use our previous knowledge or skill and apply it to learn any new task. It saves time and resources. Similarly, in AI, this concept is called transfer learning. You train computer vision algorithms to classify several kinds of images, and later you can use the trained neural network to further fine-tune and classify any new category with just a few samples and minimal training time. Similarly, natural language processing algorithms can be trained with just sentences to gain general-purpose language learning, and later fine-tuned for specific tasks, like finding whether a review is negative or positive, etc. with just a few training samples and minimal training time. Transfer learning or fine-tuning is a revolutionary concept in AI that lets us train a new AI algorithm with just a few samples, saving cost and time. It is a widely used concept in AI. Because of this, even smaller companies like early-stage startups can build AI models with very little training data and compute resources.